This video is a rehearsal of my talk, which I will give today's workshop on orthogonal modules and homological dimensions. So let's start. I will talk about orthogonal modules and projectively Wakamatsu modules. And before that, I have to mention title of today's my talk. And in the title, I write projectively Wakamatsu modules, but for some reason, today I will talk about injective dual side, injectively Wakamatsu modules. And the next thing is Wakamatsu tilting is a bit long, so I always write like double tilt. This means Wakamatsu tilting module. So I will write in this right part, and this left part is just a copy and the previous slide. So I will write in this way. So let's start with the overview of today's talk, or I will write some big figure here, which is a hierarchy of full rank, a kind of full rank. It's not strict in the strict sense, full rank orthogonal modules. So orthogonal module is the theme of main topic of this workshop, and trivially there is a very typical example, which is lambda itself, and which is progenerator, and d lambda, the matrix dual of lambda, which is injective cogenerator. We have these two extreme orthogonal modules, and we can generalize these modules like so tilting modules. And here tilting modules, I don't assume that projective dimension is at most one, so arbitrary finite projective dimensions. And we can consider cotilting modules with finite injective dimension. I will record this later. And so the figure looks like this. So this is projective side, and this is injective side. And they are dual to each other in the sense that they precisely correspond under the k-dual functor. Then the main topic is a notion of a special Wakamatsu tilting modules, which I will explain. And here, there are two dual notions, which is already in my the title of my talk. The projective side is projectively Wakamatsu tilting module. So this is a kind of full rank module which generalizes tilting modules. And the dual notion is injectively Wakamatsu tilting module, which generalizes cotilting modules with finite injective dimensions. And they are dual to each other. And as the name suggests, both are special cases of Wakamatsu tilting module. And these two concepts are now ones which I introduced in the paper. And I want to remark that in my preprint, it's called Wakamatsu projective and Wakamatsu injective, but I will change the name to this more precise name. And so this we have a kind of generalization. So the projectively Wakamatsu tilting modules is kind of generalization tilting modules to allow infinite projective dimension. And this is infinite injective dimensions. So these should satisfy finiteness of homological dimensions, but these are generalized with respect to this such a kind of restriction. And as this figure suggests, Wakamatsu tilting modules is self-dual notion, and this is very important viewpoint. And so these projective side and the injective side can be unifiedly treated by Wakamatsu tilting modules. And today's talk is concentrated to injective side for some reasons. And this is today's topic. I will talk about this cotilting modules, injectively Wakamatsu tilting modules, and Wakamatsu tilting modules. This is today's talk. So in this talk, in the rest, I will explain cotilting modules, injectively Wakamatsu tilting modules, and Wakamatsu tilting modules, and motivations behind these concepts, and state my main result. So this is overview. And so let's go to the body section, and I start with setting of today's talk. So I always note lambda by a finite dimensional K algebra over a field. And as usual, mod lambda denotes the category of finitely generated right lambda modules. I only consider finitely generated modules. And the key concept or useful concepts is progenerator or injective cogenerator inside a subcategory of module category. So I will define it first. So let C be a subcategory of mod lambda. Maybe I have to assume that C is closed under extensions, or maybe if you know exact category, I will write the progenerator and the injective cogenerator for exact categories. An object P of C is a progenerator of C. So we also progenerator relative to C, not mod lambda. If first extension group from P to any object in C vanishes, and second is enough projective situation, which means that for every object X in C, there exists a short exact sequence, which is a kind of projective cover and first CCG of X inside X. So we assume that this X, or X prime also belongs to C, and P0 is direct sum and of finite direct sum of P, so in at P. So this is a relative progenerator inside a subcategory of module category. And dually for injective cogenerator of C. I will omit the definition. So maybe it's the more natural notion is the progenerator for exact category, and injective cogenerator for exact category, but I will I won't assume the knowledge of exact category. So this is just definition of for a subcategory of module category. And I will explain about Wakamatsu tilting theory first. Maybe this is not so famous compared to usual classical tilting theory or tilting theory in terms of derived category. So I will begin with defining two subcategories associated to orthogonal modules. So let T be orthogonal module. Here, orthogonal is defined by, so it's just recall, so vanishing of all higher self-extensions. Associated to any orthogonal module T, we can consider two subcategories of mod lambda, which plays a very important role throughout this talk. XT and PUPT, these are subcategory of mod lambda by the following requirements. So PUPT is maybe X perpendicular category, so maybe sometimes written like this. This is easier to define. So X belongs to PUPT if all higher extension group from X to T vanishes. This is easy. So this consists of modules such that T behaves like injective object in that category. And similarly for XT, but this is more strong condition. So X belongs to XT if so there are some conditions. So I will write in next page. First condition is X should belong to this PUPT. And second condition is a kind of injective resolution of X, the existence of injective resolution. So namely, there exists a long exact sequence beginning from X, and all the terms are T. Which I write star, and such that this should satisfy some assumptions. So all the terms are at the T, and we may assume another assumption. So by applying blank T factor, so if T is injective, this is the exact factor. So this should be exact, and I require it. So this remains exact. So this is a kind of injective resolution of X, where injective object is T. This is a definition of two subcategories. And maybe so I will explain examples of these two subcategories. So first, trivial example we should mention is the case of injective cogenerator. Then these subcategories coincide, and this is mod lambda. This is because the lambda is injective, so any extension group from X to the lambda vanishes for every module X. And this is also mod lambda because every object has injective co-resolution. So this is a classical case. And I will explain another important example which related to Greenstein homological algebra. So consider x lambda, which is a kind of object which can be co-resolved by lambda. And this is actually coincides with the category of Greenstein projective modules. And I want to explain details about Greenstein projective modules, and maybe this will be the main topic of Brune Marcintik's talk. So this category naturally arises in the study of Greenstein projective modules, and this category can be a generalization of the study of this category. So the basic idea is that these two subcategories, in these two subcategories, T behaves like injective object and injective cogenerator. And this can be made precise by the following proposition. Or theorem, maybe. The first is, so let T be orthogonal modules. The first is that about our property. So lambda is a progenerator of property. This is relatively easy to show. But in general, and so I will write here, T is an injective cogenerator of xt. And this is a little hard. And actually, these kind of things and these subcategories are first studied by Austrander Wrighton's paper, 1901, applications of contravariantly finite subcategories. And this is one of their results. So I will summarize this in the following table. This table plays a important role, important viewpoint from today's viewpoint. So for orthogonal module T, we can consider two subcategories, xt and pub-T, and this is contained in this. And the above theorem says that this is always lambda and this is always T. So there are two missing parts here and here. So in general, lambda may not belong to xt. So we expect that this is lambda and this is T, but this is not necessarily true. There are some counterexamples. And the motivation is to fill this table. And the first thing is I want to recall is that theory of cotilting modules, which is established by Austrander. So let T be a lambda module. A lambda module is cotilting module with finite injective dimension, not only just one. If T has finite injective dimensions and T is orthogonal modules. And third condition is a kind of generating condition. it says that there exists a finite exact sequence which resolved injective cogenerator d lambda. So this is a dual of tilting modules. So d lambda can be resolved, finitely resolved by add t. This is the definition of cotilting modules. And one of the result of our lambda writing is that if t is cotilting, then these we can say a bit about these two subcategories. This is one of the results. If t is cotilting, then they show that these two subcategories coincide. In particular, so this coincides, so these becomes equal. So in particular, so the result implies that they have progenerator lambda and injective cogenerator t. So if t is cotilting modules, then these subcategory coincide. This is a very important because xt is a little difficult. So let's look at the left page. So xt is defined by the existence of infinite long exact sequence. So it's obviously difficult to calculate the first conditions, and also on the right-hand shows that these are equal if t is cotilting module. So this is our cotilting theory, and I will move to Wakamatsu tilting theory. So let's define Wakamatsu tilting module. Wakamatsu tilting, but I write double tilt Wakamatsu tilting. If the first condition is t should be orthogonal module, the second conditions can be easier to understand if you look at this table. So we want this to lambda and this to t. And Wakamatsu tilting module is one such that this is lambda. So the simplest definition is that lambda belongs to xt, but by assumption, under assumption one, this is equivalent to that xt as progenerator lambda, or maybe lambda is a progenerator of this xt. So let's look at this table. So this definition of Wakamatsu tilting module says that this is lambda if and only if t is Wakamatsu tilting. You can think this as a definition of Wakamatsu tilting module. I will write some example of Wakamatsu tilting modules, and by the above theorem of us on the writing, every cotilting module is Wakamatsu tilting module. So we have this inclusion. And second is more important. A lambda module, right lambda module T is Wakamatsu tilting if and only if its K-dual, which is left lambda module, is Wakamatsu tilting. So Wakamatsu tilting is self-dual notion. This is very important. This is not obvious, but proved by some homological algebra and ring theoretic observation. In particular, so the dual of cotilting module is tilting modules. So in particular, tilting modules is also Wakamatsu tilting module. And I want to remark about lambda itself. Lambda itself is Wakamatsu tilting module. This can be proved by the second implication or directly, because clearly X lambda satisfies lambda, contains lambda. It's easy to see. So lambda itself is a typical example. And in this case, I will call that X lambda is Gorenstein projective modules, the category of Gorenstein projective modules. So the motivation is that for given orthogonal modules, we want to construct a subcategory of mod lambda in which this orthogonal modules behaves like injective cogenerator. And actually, this says that the definition of Wakamatsu tilting says that if a given orthogonal module is Wakamatsu tilting, so I write corollary, if T is Wakamatsu tilting, then this is it's just a replacement of definition, but this category XT has progenerator, lambda, and injective cogenerator, T. So we can construct such a subcategory of mod lambda in which T behaves injectives and lambda behaves projectives. And actually, this is this construction is a little artificial, but this is very this is in some sense all of such a construction. So I want to remark other remark about that. So consider a pair of progenerator and injective cogenerator. Pair Pi such that P is progenerator and I is injective cogenerator of some exact category, or maybe if you know exact category, this is just an extension closed subcategory of some routine algebra. Extension and so more precisely closed under extensions and direct summands for some routine and some finite dimensional algebra, gamma. So consider such a subcategory, and the gamma may move defined gamma. We consider defined gamma and consider all such pair. Then the above corollary says that for a given Wakamatsu tilting module, if this is a Wakamatsu tilting module over algebra lambda, then lambda T is such a pair. So we can construct an extension called subcategory of mod lambda. This is XT, which has progenerator lambda and injective cogenerator T. And surprisingly enough, the converse holds. And this is a result of my first paper about Wakamatsu modules. Conversely, for any pair, any such pair, or progenerator of injective cogenerator of some exact category, we can, this pair is kind of equivalent to a pair arising in the first one. For some algebra lambda and T lambda, this is Wakamatsu model. So Wakamatsu module is very natural from the viewpoint of exact category or subcategory of module category, because it behaves like a universal injective cogenerator. So this is an interesting viewpoint, I think. Wakamatsu is a universal injective cogenerator. The construction is that we consider the endomorphism ring of P, and this becomes lambda, and then injective cogenerator becomes Wakamatsu models over the endomorphism algebra of P. So Wakamatsu models are very natural from the viewpoint of such considering pair of progenerator and injective cogenerator of general extension cross subcategory of module category. This is Wakamatsu theory, and I will move to the definition of injectively Wakamatsu modules, which I define. I will, maybe I should write right here. Let T be a lambda module, and I call T a lambda module T injectively Wakamatsu if so. Maybe it's better to look back to this table again. I have one missing point, and this is the definition of injective Wakamatsu. So if T is an injective cogenerator, so first T should be orthogonal module, and second T is an injective cogenerator of perp T. So the missing point. So this definition says that this is T if and only if, or its definition, T is injectively Wakamatsu. Oh, I forgot about IWT. So injectively Wakamatsu is also wrong. So I write IWT. So the definition is natural if we consider such a table left. This is the definition. And from the definition, we can easily prove that T is injectively Wakamatsu if and only if T is Wakamatsu and two subcategory coincides. So XT coincides with perp T. So as I mentioned before, if T is cotilting, then these two subcategory coincides. And so in general, this category may not coincide even if T is Wakamatsu tilting. So for Wakamatsu tilting T, this is a very nice condition because xt is complicated. And so injectively Wakamatsu tilting consists a nice subclass of Wakamatsu tilting module. And also, I have this cotilting module is an example of injectively Wakamatsu tilting modules. So the first example is already written above. Cotilting module is injectively Wakamatsu tilting module. But in general, injectively Wakamatsu tilting module may have infinite injective dimension, but this has infinite injective dimension. So this is a proper generalization. And the second example is about lambda itself. This is Wakamatsu tilting, but this is IW tilting, injectively Wakamatsu tilting, if and only if, so by the above proposition, x lambda coincides with pop lambda. And if you remember, this is the category of Gorenstein projective modules. So the condition is that the category of Gorenstein projective modules coincides with the perpendicular category of lambda. And such an algebra is called weakly Gorenstein algebra. Lambda is weakly Gorenstein. And this is the main topic of Martin-Jacobs talk. So it's injectively Wakamatsu tilting related to Gorenstein homological algebra in this way. And I maybe so I will explain my results about these Wakamatsu tilting modules. So so this is this, so maybe this. So I will talk about main results. So before that, I want to recall classical result of tilting module. This is by essentially due to Bongard. He proved a kind of completion for classical tilting modules. So let's state in cotilting case. So let T be orthogonal module with so his results say that T is cotilting module is injective dimension at most one, if and only if it has finite injective dimension and orthogonal. This is the same as the definition of cotilting module. Sorry, we have to modify this. And the third condition is in the definition of cotilting module, we have to construct an infinite resolution, finite resolution of the lambda by add t. But this can be replaced by just counting the number of indecomposable objects, indecomposable summands. So this is the number of indecomposable summands of t, direct summands of t. So this gives a very convenient numerical condition of cotilting module or tilting modules. And this is because this is clearly easier than constructing resolution. So this is easier, much easier than the existence of or sorry, maybe in this case, three-term exact sequence, short exact sequence. But this only works for, so the result, this result depends on the completion. Completion of cotilting module into partial cotilting module into cotilting modules. But this only works, completion only works for classical case. So there is a counterexample. There are some counterexample with injective dimension greater than or equal to 2, such that partial cotilting module cannot be completed to cotilting module. There exists a counterexample. But so I want some similar theory for self-orthogonal modules, so without any finiteness condition of injective or projective dimensions. But this says that such a thing is very hard in general. But the motivation is that, at least for representation-finite case, so the first thing I have, we have to consider about homological theory is considering representation-finite case. And my main result is about such a case. And so I can write main result here. Suppose lambda is representation finite. So there are only finitely many indecomposable modules. Then first thing is that we can have a completion for any orthogonal module. There exists some module such that direct sum is injectively Wakamatsu, or maybe this can be replaced as just Wakamatsu. So any orthogonal module of a representation finite algebra can be completed to Wakamatsu module. So it's nice. So completion holds works for representation finite case. And the second condition is about the equivalence of Wakamatsu modules, characterization of Wakamatsu modules for representation finite case. So the following conditions are equivalent for lambda module T if lambda is a representation finite. The first condition is injectively Wakamatsu. The second condition is just T is Wakamatsu. The third condition is precisely this condition. T is orthogonal such that it has full rank. So the number of indecomposable summand is equal to the rank of the algebra. The fourth condition is a maximality condition. So T is maximal orthogonal. This means that T is orthogonal. And if direct sum is also orthogonal, then M should be already contained in at T. So we cannot extend T into a bigger orthogonal modules. So maximality condition with respect to orthogonal modules. This is the main result of today's talk. So if we assume that this is strong assumption, lambda is representation finite, then any orthogonal module can be completed into Wakamatsu modules. So these are same by second. And second gives a characterization for Wakamatsu module. And third and fourth conditions are very convenient because we don't have to compute about a kind of this kind of condition. This is very hard. So this is main result. And I will deduce some corollary from this main theorem. So let lambda be representation finite. So my result can be applied to the study of orthogonal modules over such an interval. The first statement says that if lambda module M is orthogonal, then the number of indecomposable summand is bounded by rank of the algebra. The second condition is that if this is Wakamatsu, so it satisfies these equivalent conditions, then representation finite case, then these two subcategories always coincide. And third is just a corollary of 2. If lambda is representation finite, then the category of Gorenstein projective module is coincides with this X perpendicular category. So lambda is weakly Gorenstein if lambda is representation finite. So in general, I finished my talk with suggesting some homological conjectures related to this main theorem. And in particular, there are some related conjectures, which is related to my main theorem, and also related to classical homological conjectures like Alstrand-Writing conjecture. The first is about the first of this corollary. This is called boundedness conjecture by Happel. Happel's some proceeding of some conference. If lambda module T is orthogonal, then the number of indecomposable summands should be bounded by the rank of the algebra. I think this is a little strong conjecture. But as far as I know, there is no known counterexample. The second is about, so I have to remark that some of the conditions are not equivalent for representation infinite case. But some should be whole, I conjecture. One of such is Proje equal Inje conjecture. So this name comes from the fact that Wakamatsu module is a universal injective cogenerator. So a lambda module T is Wakamatsu. If Wakamatsu, then the number of indecomposable summands should coincide with the rank of the algebra. So let's recall our observation about Wakamatsu theory. So where is this? So this kind of conjecture is related to the conjecture about exact category in general. So if P is progenerator and I is injective cogenerator of some exact category under some assumption, then the number of progenerator in projective objects coincides the number of injective objects. So this project conjecture is equivalent to such a conjecture about subcategory or module category. The final conjecture is about the maximality condition of Wakamatsu module. Maximal orthogonal conjecture. It says that if T is Wakamatsu, then T should be maximal orthogonal. And we can consider weak version, which only consider injectively Wakamatsu or projectively Wakamatsu. And these relation between these conjectures looks like as follows. Boundedness conjecture implies other two conjecture, Projet-Inje conjecture and maximal orthogonal conjecture, and this trivially implies weak version about injectively Wakamatsu or projectively Wakamatsu. And this implies this, and this is equivalent to also underwriting conjecture. Which appear in the maybe previous talk. This says that lambda should be maximal orthogonal. This is one rephrasement of also underwriting conjecture. So we cannot extend lambda into orthogonal modules in non-trivial way. And one of the corollary of my main result is that these conjectures are true for representation-finite case. And I stop here. Thank you for listening, watching this video.